All right, welcome to part 3 of the lecture. Today we're talking about Big O, the anime. No, wait, Big O, the computer science term. So I've kind of held off on defining Big O sort of mathematically for you guys. I've kind of told you guys in plain English how it works. Um, Before I've said things like, if you've got a million people in your vector and you insert something at the beginning, you've got to move all million elements to the right. So that'd be an order n operation because n is the size of the vector. Um, n is the amount of work you have to do if you have to move everybody to the right. So there is a more formal way of defining big O, and that is n is the problem size, t is the amount of time it takes. And let's say that you've got a big O n squared algorithm. That means, roughly speaking, the running time is going to increase proportional to the square of the number of elements in your problem size. Now, what's interesting about this is that there are some algorithms like let's say like selection sort or something like that. Selection sort is stream is paused. There we go. Okay, so selection sort is an order n squared algorithm. It's not good. But what's really interesting, if you like zoom in on this area over here, if you're talking about problem sizes like less than 5 or something like that, like selection sort's actually faster, than like an order, like a provably optimal order n log n algorithm, which includes things like merge sort, heap sort, and quick sort, things like that. And so the standard library actually uses different sorting algorithms based on the problem size. So if you pass it a very small problem, like sort these two guys, it'll just do a comparison, like, okay, that one's bigger, swap. It doesn't actually do the whole algorithm for quick sort and all these things, because a lot of them involve, they got to construct a heap for heap sort, and for merge sort, it creates two separate, vectors, and it's got to initialize those and copy them in, and then sort them, and then copy them back. And for really small problem sizes, it actually can happen that your order n squared algorithm is actually faster than your linear normal, whatever it's called, your order n log n algorithm. And so for very small numbers, you can actually have better performance on a n squared than a n log n. In fact, the standard library usually does that. It uses a very fast order n squared that just doesn't have all the overhead that the n log n has. And that's a really ugly n log n. So let's try drawing this a little bit better. So yeah, whatever. Cool. So what does it mean, like mathematically, though, when you say that the running time of something is order n squared? What it means is that past some point, like let's say past 5, but it doesn't matter. You can pick any point you want. There is a curve for k times n squared that is always above it. And there is a curve for m times, I did k again, didn't I? Don't look at the k when you're writing an m. Pro tip, m times n squared, that is always lower than it. And these k and m values can be anything. It doesn't really matter. So this could be like 100 n squared is always going to be bigger than this guy, and 2n squared is always smaller than this guy. Okay, so the k and the m actually don't matter. All that matters is that it is possible to find some number for k and some number for m, where the one is always above the running time of this algorithm, and this one is always below the running time of this algorithm. In other words, they bound the running time of your algorithm, whatever, let's say it's Michael Bublé sort or whatever like that, and you're doing bubble sort, you can find some constant here that will always take longer to run than bubble sort will, and some constant for m here that will always take less time to run than Bublé sort here. And there you go. That's what it means to be order n squared. It is bounded on both sides by n squared curves. Okay. I usually don't teach it like that. I like using English instead of math, but I had some students ask, like, what's the actual definition of big O? And that's basically what it means. And the reason why this works is because this is true for all numbers bigger than z, right? So for all numbers past this point, it is bounded. And so if bubble sort actually happened to be like n cubed, it doesn't matter what value for k and m you pick. At some point, if bubble sort was n cubed, it would explode out of that n squared bound. For any value of k, it doesn't matter what value k is, Kevin. It really doesn't. Like, you can pick 100 or 1,000 or 1,000,000, it doesn't matter. At some point, if you have like 1,000 n squared and you've got n cubed, at some point for n, this value here is going to be bigger than this value here. It does not really matter which value for 1,000 you pick. There's always going to be a point at which the n cubed is going to break through the enclosing curve to the north. Does that make sense? You don't actually have to come up with a number here, really, in most cases. And in practice, when you say, what does an order n squared algorithm look like? It means a doubly nested for loop. Is what it means, like, in reality. So if I switch back to the server, let me see if I can break Discord again. It's been crashing all day. Switch back to over here. Then is k the amount of ints? No, it's just some constant. All you need is some constant for k and for m, and no matter how big n gets, those numbers will bound them from above and from below. In practice, what an order n squared algorithm looks like is this. So, how many times is it going to print hi to the screen? $1 million, right? For every count of I, when I is 0, j goes from 0 to 999. J does 1,000 couts of I. And then I goes to 1. And then we do 1,000 couts of I. And then I goes to 2. We do 1,000 couts of Y. So 1,000 times it does 1,000 work for a million. So this is an order n squared algorithm. Okay. And the actual details don't matter. Like, a lot of people get like hung up over like, what if we did a cout inline here? You know, that's an extra 1 everything. We don't care. We don't care. We really don't. Like, Big O is a very coarse grained analysis of how long algorithms are going to run. And the reason why it's so important, and the reason why the details don't matter, is because here you're talking about the difference of like 0.1%, right? So 1 out of every 1,000 times you do 1 extra operation. Now, the inline might, and in fact probably is, more expensive than a pure cout by itself, but we're also doing inline there. So yeah, you're talking about like an insignificant, fraction of a point. Nobody cares. The reality is, if you have the wrong Big O, right? Like, let's say you're doing vectors and you're inserting constantly at the front of the vector. You're doing order n work every time instead of order 1 work every time. And so if you do this n times, your algorithm is going to be n squared, right? So if you have a vector, right? You have a vector, and you say 1 million times insert at the beginning of the vector versus 1 million times insert at the end of the vector. How many different what's the difference in operations here that we're talking about? Like, let's say each one of these operations takes 1 second. Because we screwed up, right? We should not be repeatedly inserting at the beginning of a vector. This is the wrong task for the wrong data structure. The entire point of this data structures class is so that you know which data structures you should use for which problems. If you constantly have to insert at the beginning, you want to use a deck or you want to use a list, right? If you want to insert constantly at the end, the vector is the best choice. Okay. If you have to insert in the middle, a list is the best choice. If you're repeatedly inserting in the middle, maybe. You have to know these things because let's compute this. Okay. Inserting at the beginning of a vector is order what? If you have 1 million people in a vector and you want to insert into slot 0, you gotta move everybody. So how many operations do you have to do if you're inserting at the beginning of a vector? What's the big O on that? Good. It's order n, because you have to move n people. That n is the size of the vector out of the way. You might be like, well, on average, it's n divided by 2. Yeah, nobody cares. Like, oh, it's twice as fast. Oh, that's cool. Like we're talking about differences of like in 5 orders of magnitude, like times 2, like nobody cares. So, order n times. So 1 million times, we're doing 1 million work. And let's say it takes 1 second just to make this exaggerated. How long does it take to do it the wrong way? How many operations to do it the wrong way? If you do 1 million inserts at the beginning of a vector, 1 million's not even that many numbers, right? It's not really that many. It's not order 1. It's order 1 if you insert at the end. If you're inserting at the beginning, Jarek, it is order n. But 1 million times, we're doing 1 million work. Yep. So if there are 60 seconds in a minute, and 60 minutes in an hour, and 24 hours in a day, and 365 days in a year, because we chose the wrong data structure for the job, because we chose vector instead of list, it is going to take 31,000 years to finish. If we did it instead, versus, all we have to do is change one word, right? Vector to list. Like just that one word change. Let's see how long it takes now. Inserting at the beginning of the list is order 1. Okay. You got a pointer to the beginning of the list, just add the new thing to the front of the list. Easy. One million seconds divided by 60 seconds in a minute, divided by 60 minutes in an hour, divided by 24 hours in a day. So it's 11 days. Now, 1 second per operation is obviously very small to exaggerate the effect, but you're talking about the difference of 11 days versus 32,000 years. One of these you might be willing to wait for. 32,000 years ain't nobody got time for that. And that is a massive, massive difference. You were doing 1 million times the work because you didn't know the right data structure for the job. You guys understand? This is the thesis statement for this class, is you have to learn the basic data structures and we have you write them so you understand them. Like internalize them better. But inserting at the beginning or the end of a list is order 1. Or in the middle. If you have a pointer there, inserting in the middle of the list is order 1. It's the best thing that lists are good at. It's inserting in the middle. Inserting at the end of a vector is order 1, and inserting anywhere else is order n. So you're talking about, and 1 million's not even that many numbers. It's really not in terms of greater scheme of things. 1 million's it's substantial. It's not that big. But you're talking about 1 million times slower because you changed. Because, all you're familiar with is vectors, right? You're like, just use a vector for it, right? All you did was change that vector to a list. Your code now runs 1 million times faster. And that's why we don't care about things like, oh, it's twice as fast. No, we don't care. Like, do you want to wait 32,000 years or 16,000 years? It's still terrible. it's still horrible. Like, nobody wants to wait 16,000 years for your stupid program to finish, right? Oh, it's twice as fast. Great. That's neat. Oh, you turn the optimizer on and it finishes in only 10,000 years. Cool. No, like, nobody cares about that. The single most important thing that you can do for optimizing your code is picking the right data structure and the right algorithm for the job. The big O is the single most important thing when it comes to running performance of your code. You have to make sure you have the best, most optimal big O time possible before you even start looking at other things like turning on the optimizer and, are you doing call by reference or call by value? Are you doing unnecessary copies, things like that? Doing profile guided optimization. Now, if your big O is wrong, you're toast. That's it. It's game over. You're going to be waiting to the heat death of the universe to finish your application. Okay. So let's talk about what each data structure is good at. Okay. So vectors are good at what? What are they good at? Stacks and queues I'm not even going to throw in here because a stack is a vector and a queue is a list, let's say. So what are they good at? When do you use them? Reminds you of the C for it? Yeah, there's a reason why it's on it. So vectors are good at inserting them in. That's their clutch thing. They have order one, insert at the end, performance. Searching's not great. Searching's order in, deleting's order in, except at inserting and deleting in the end. And they're basically order in everywhere else. Lists are good at order one, inserts and deletes if you have a pointer to the place. Okay. So if you have a head pointer and a tail pointer, inserting at the head, which we call push front, inserting at the tail, which we call push back, is order one. It's really easy. You got a pointer there? Oh, new thing, hook up the pointers, done. You're like, but wait, it's 4 operations because you have the next pointer, the previous pointer, and the data is set. No, nobody cares. Nobody cares. What we care about is, in order to insert at the end of the linked list, did we have to go through all trillion elements in the linked list to get there first? If we did, that's a stupid linked list. You could write it that way, and I've done it before. But it's a stupid linked list. If all you have is a head pointer and no tail pointer, you can make it work. You can. You just, every time you insert at the end, you start at the head and you go to the next, 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 you go to the next. And, you sit around, you wait a while, and a trillion go to the next later. You're at the end. Congratulations. Append 1 to the end. You're done. It's an order in operation. N is the number of nodes in the linked list. You guys understand that? That's what big O is. N is how many people are in your linked list. If you don't have a tail pointer, then inserting at the tail takes an order n traversal to go through the entire damn thing to get to the end. It would be like going to the phone book and be like, all right, write my name at the end. And you start at the beginning and you read every name in the phone book until you get to the end of the book instead of just opening it to the end, right? It's stupid. If you don't have a pointer somewhere, like if you want to delete from the middle of the list and you don't have a pointer there, it's going to take an order in traversal together. But if you have a pointer there already, like let's say you're making like a word processor or something, you got a cursor there. You just type, insert in the middle, insert in the middle, insert in the middle. Hello, world. Can't do that with any of the other data structures. Vectors would be order in every time you type a letter. Do a million operations every time you type a letter. Lists, you just have the cursor there, and then you can type away to your heart's content. BSTs can't do it at all because BSTs would sort all the letters you typed. And you have, here are all your A's, here are all your B's. Is this James Joyce? I don't even know what's happening anymore, right? So BSTs are good at sorting. BSTs are good at searching, absolutely. Searching a list is order in. Their order is 0 for sorting. BSTs are the king. They're always sorted. You don't ever have to sort a BST. done. You can't even call sort on. They're done. They're sorted already. It's great. And they have insert. Let's say balance BSTs, right? Because unbalanced BSTs are bad. They're just bad at everything, right? So unbalanced BSTs are horrible. They're like linked lists that don't have a tail pointer, right? Because if you insert 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 into an unbalanced BST, you just have now created a singly linked list with extra steps with no tail pointer. And so if you want to insert 11, you have to go down to the right, 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 to the right. You have to do an order in traversal to find the end spot and put the 11 on there. They're terrible. Don't use unbalanced BSTs. Every standard library BST, the set class, is balanced. Okay, you'll learn how to balance them in your junior year of computer science. All you need to know for now is that they auto-balance themselves somehow. Okay, insert, search, delete is order log n. A log n is actually really fast. A lot of people don't understand this. If you are doing like game dev, and game dev is very sensitive to time, right? Because gamers want the most frames per second possible. So if you have 60 frames a second, you're given a 60th of a second, right? And if you add even like 10 milliseconds delay onto every frame, you're going to drop from 60 frames a second to 27 frames a second. And nobody will play your game. Look at Dragon's Dogma, right? So the thing is, like, a log n algorithm is fast enough for gaming. So in gaming and graphics and the different algorithms, computational geometry kind of stuff that goes under the hood in game dev, if we get an algorithm that's order log n, we're like, that's good. That's fast. Because every time you double the problem size of an order log n, you only do one more step. That's really, really fast. So you go from 1 million to 2 million people in your game. Oh, it takes one more step. We go from 2 million to 4 million people. Oh, it's one more step. It's now 22 steps instead of 21 steps. We just added 2 million players. We doubled our player count. And instead of finding any person in 21 steps, it now takes 22 steps to find them. Oh no. It's so horrible. Right. Everything a balanced BST does is order log n. Except for sorting. They're always sorted. Great. Hash tables are good at insert, search, delete, and they do this in order one time. In a single amortized order one time. In a single operation, on average, a hash table will be like, here's your data. That's good. It's pretty good. Where if you have 1 million people, it takes 20 steps to find somebody in a binary tree. Hash table can find it in 1 step. 20 times faster than what's already considered pretty damn fast. Like I said, order log n. Like, log n is really, really fast. Like, nobody cares. Like, if your algorithms log in, right, good. You're done. Like, that's great. Now, if you have a easy way of making it order 1, yeah, go for it. 20 times faster if you have 1 million. But log n's already pretty good. It's already 50,000 times faster than order n. Right, searching for a name in a list or a vector takes 1 million steps for 1 million names. Binary tree takes 20. It's 50,000 times faster. So, but again, an extra 20 times speed. Yeah, cool, good. It's good. So let me show you guys how to do a hash table real fast. Okay. So the BST class is called a set. So if we have a set of integers named +1, we can insert into a set by using insert. So we insert 10, and 100, -10, and -420, and 960, and whatever. Insert some numbers. This is all insert. We can do search by saying fs.contain. 431. Scout. 431. And then we do delete. We do s1 dot erase. We erase. Then insert. Search. And delete. These are the three big things we care about in every data structure. How long does it take to insert? How long does it take to search? How long does it take to delete? All of these are order log n, because set is a BSD. And then if we want to print everything, we just use our regular old range-based for int x equals, for every integer x in S1, now, hash tables. We're not going over how to make them today. We'll just go over how to use them today. Okay. And make an unordered set. And this guy, instead of being called S1, is going to be called S2. Why not? Okay. And there we go. So if we look at the code here, printing, yeah, basically printing is going to be always ordering. And this is actually kind of an important thing. If you ever have an algorithm where like the heart of your algorithm is order n, it's kind of free, because at a certain level you have to just read all of the data off of disk anyway, right? Like let's say that you've got a database with like 100,000, like a text file containing like 100,000 chess players. And one of the operations you want to do is find the person with the highest elo. As you're reading the data, right, searching through that is an order n search, right? You find the person with the highest elo. But here's the thing, like as you're loading the data, you can just keep being like, hey, is this the person with the highest elo? No. Oh, look, Carlsen Magnus, right? And you can just almost get it for free, right? Instead of a separate order n operation. Most algorithms, now it's not true. Sometimes you have all the data already loaded up and things like that. But like a lot of programs, you have to load the data, do some operations, and then print the result. And so if your main algorithm that does the analysis is order n, it's kind of free because you have to load the data anyway, which is an order n operation. So, a lot of times you just do it as you load it. Like, are you the greatest elo? Are you the greatest elo? Oh, you are. Great. Oh, I found a bigger one. You just do it as you load it. And it's essentially like there's no extra cost over the time it takes. Because loading from disk is usually the slowest part of every program like that. Where you have hard drives, even SSDs are not that fast. And getting the data off of mass storage is actually usually the slowest step. And so if you just do things while you're waiting for the hard drive to feed you more data, it effectively has no cost. So anything at the order n level like that doesn't bother me. If you're doing like batch processing of data and things like that. But if you have like a video game and everything's loaded into RAM already, you don't want to do an order in like, would be an example. Like you have a grenade go off. You don't want to go through every person in the world and be like, are you within 10 meters? 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 Because that's stupid. You should have an acceleration structure that will tell you everything within 10 meters. But depending on your task, order in doesn't bother me. But sometimes it will. Okay, so yeah, printing all the data, order in. And so a lot of times you just, ultimately your program is going to be order in because you have to load the data and print it. So, here's the result from our set. Here's the result from our unordered set. Okay, you can see the unordered set is unordered. The data is not held in sorted order. But the set always is. You see that? The set always holds the data sorted. The hash table does not. And so the BST has an insert time of order log n. Search has a search time of log n. Delete has a delete time of log n. Printing is order n. Right? Basically, anytime you iterate over all the people, it's going to be order n. It's not a lot you can do about that. The hash table, inserting is order 1, yay, optimal. searching is order 1. Deleting is order 1. Nice. And then printing is order n. And if you wanted to, you could do everything in the hash table, and at the very end, you could pull it out, copy it into a vector, and sort it if you wanted to. And whether or not that's going to be faster than just using a VST all along, depends. Depends on, benchmark it, see if it's faster. It might be. I like hash tables. The only downside to them is that they don't come out sorted. Hash is a quick access tool. Yeah, fastest search, fastest delete, fastest insert. Done. They are great. They are my jam. The two data structures that I actually use all the time are vectors and hash tables. Everything else is in there for like special needs. Decks are there if I need to insert at the beginning of a vector. Cool. I'll use a deck, but don't have to with that one. Lists are there if you want to insert in the middle. How often does that happen? Not often. Sometimes though. The Josephus problem, which we might be doing with you guys, it's great for deleting from the middle. You need to know these things so you have all the tools in your pockets. But the two big ones, it's like chocolate ice cream and vanilla ice cream. They're the base for like everything that I do most of the time. You want to still have your butter pecan, your strawberry, whatever. But your two like go-to, most important ice creams for building the sundaes of your dreams, I don't know where I'm going with this, are vectors and hash tables. Okay? Vectors keep the order that you put things in them. Hash tables, very fast insert, search, and delete. And sometimes I'll use both. And it's great. And that is our lecture for today. So we went over a lot of stuff today. The code is up in the let's see here. Main.cc public O positive. So if you want a copy of the source code from today, it is in /public/O positive. Toss this up on Discord for you guys. I hope you guys enjoyed the lecture today. You guys had a great Easter. I'll see you guys next time, where we'll be maybe getting a lecture about music and Discord. Actual Discord, not Discord. But actual musical dissonance. So it'll be pretty exciting. All right. See you guys. Peace.